Okay, good afternoon, everyone, and welcome. My name is Thomas McKenney. I am a ship design manager at the Mærsk Mc-Kinney Møller Center for Zero Carbon Shipping. And as the leader of the NoGAPS ship design project, I'm happy to be the moderator for today's webinar. Today will be a little different from the typical discussion on ammonia shipping. We will not be on the surface and talk in generalities, but we will instead deep dive into specifics on ammonia-fueled ship design, including the reveal of the NoGAPS ship design concept. NoGAPS is a ammonia-fueled gas carrier that can also carry ammonia as a cargo, and it could be among one of the first ammonia-fueled vessels in operation. Today's webinar will also highlight the role of gas carriers as the shipping segment best positioned to introduce ammonia as a fuel. I will now provide a brief overview of the NoGAPS project and introduce the lineup of presentations and panelists for today. NoGAPS, or the Nordic Green Ammonia-Powered Ship, is co-funded by the Nordic Innovation Fund and consists of project partners that include the Mærsk Mc-Kinney Møller Center for Zero Carbon Shipping, Global Maritime Forum, Yara, BW Epicosin, DNV, Wärtsilä, and MAN Energy Solutions. We also have Danish Maritime Authority, which is the flag representative, and Breeze Ship Design as the ship designer. The first phase of the NoGAPS project ran from 2020 to 2021 as part of the first round of the Sea Meets Land mission funded by the Nordic Innovation Fund. The project developed a holistic proof of concept that addresses ship design and safety, production, and supply of green ammonia, as well as the business models needed and economic incentives required to make this project economically viable. Now we are in the second phase of the NoGAPS project, and here we are focused on producing an initial ship design concept. This will lay the foundation for a shipyard tender and potential construction of the vessel. This project brings together the essential players to source this design and is made possible by Nordic Innovation funding, as well as in-kind contributions and support by the partners. At the same time, the project would like to strengthen the connections between the NoGAPS consortium and also the emerging ecosystem around ammonia-powered shipping. And we believe this is important to leverage learnings on topics like safety, fuel handling, and bunkering. Today's webinar is one of those aspects where we want to engage the public. As we continue, further phases will primarily be defined by commercial agreements and are outside the scope of this specific phase of the project. Based on phase one conclusions, the ship design has two main objectives. The first is to confirm that there are no major technical or regulatory obstacles to getting this vessel on the water. And the second objective is related to demonstrating a credible business model through both risk and cost reductions. It's not enough to simply design a safe ammonia-fueled vessel. It also needs to be a design that can lead to a credible business model. And this is the other important aspect here as we look at the ship design. Ammonia is expected to play a central role in the industry going forward as one of the main potential fuel pathways. This here on the screen is called the Fuel Pathway Maturity Map developed by the center. And what it highlights is the current maturity level of the different pathways that are currently being investigated. Ammonia being one of those main fuel pathways, immediately you can notice that the maturity of this pathway is the lowest out of the ones identified here. There are some major challenges that still need to be overcome, and this is one of the important objectives and aspects of all the different ammonia-related projects that all of our partners are currently working on, including the NoGAPS design project. The development of tank storage solutions for larger ammonia volumes, engine and fuel cell development, these are still ongoing. Dual fuel ammonia engines are being developed, but are not finally proven or commercially available yet. We also see that potential post-combustion emission reduction technologies might be needed, but we don't fully understand the emission profile yet. On the onboard safety and fuel management side, there are certain safety-related considerations that need to be factored into the design. Ammonia is highly toxic, and this requires a number of risk assessments and understanding the impact on vessel design, and also in key cost areas. If we look at onboard safety and operations, we see currently LPG carriers able to handle safely management of ammonia as a cargo, but as a vessel shifts to also having ammonia as a fuel, there are different risks that come up, both for crew exposure from leakages or emissions, but also other impacts to the vessel and surrounding areas. This is why risk assessment, including quantitative risk assessment and other human factor considerations, are required to enable a detailed design that is inherently safe. As we continue throughout this presentation and have an open discussion with the panelists and start to answer your questions, keep in mind that this fuel pathway has potential, but at the same time requires maturation over the coming years. And as we look at the urgency of decarbonization within this industry, we need to make sure and balance the desire to mature this fuel pathway with ensuring that all the risks are properly mitigated. So with that, let's move into today's agenda. It will consist of 3 short presentations, followed by a panel discussion with the presenters, as well as some additional panelists from the NoGAPS project. We will present the latest developments coming out of the center work on ammonia safety, in particular quantitative risk assessment work. We will present the NoGAPS concept and reveal that for the first time to the public today. We will also go through the outcomes from the latest hazard risk assessment workshop, which just recently was carried out in the last 2 weeks. And then we will go through a number of questions and answers. And we ask that all of you please post your questions in the chat box throughout the webinar, and these will be addressed towards the end as part of the panel and Q&A discussion. So with that, I would like to introduce our first speaker, who is Klaus Rudhensen. He's a Senior Technology Manager at AP Møller Mærsk and also a secondee at the Mærsk Mc-Kinney Møller Center for Zero Carbon Shipping. Klaus has over 30 years experience, with the last 10 years at AP Møller Mærsk, working on and managing machinery, automation, and technology projects. He's specialized in the assessment of carbon neutral fuel solutions for shipping and is currently leading multiple projects at the center related to ammonia as a marine fuel. With that, Klaus, go ahead, take it over. Thank you.
Thank you, Thomas. Yes, I would like to present some of the initial findings from the safety study being done at the center in collaboration with the Lloyd register. The partners in the project from the center side is Mærsk, it's MAN Energy Solutions, Mitsubishi Heavy Industries, NYK, and Total Energies. And those are the partners will continue throughout the project. But in phase 2 of the project, ABS, BP, Cargill, Stolt Tankers, and V Group joined the project. So that's the total list of participants in the project as of now. Yes, the project has been, as I mentioned, run in 2 phases. Phase 1 has been completed, which consisted of actually building the quantitative risk assessment model that was done by Lloyd. And And from the center side, we provided some ammonia design of 3 selected vessel types: a container vessel, a tanker, and a bulk carrier, where we took some existing design and applied tanks and fuel preparation rooms and pipe routing, calculation of pipe sizes, and so on, in order to use a quantitative risk assessment that provided us with 2 main results: what we call location-specific individual risk, which is an illustration of where on the vessel is kind of the most dangerous place to be. So it illustrates the risk of fatality to in 1 per N for a person being occupied in that area all of the time, so to say. That's of course not the case on a vessel, so that's why the individual risk per annum is interested, and that's where we take into consideration the actual time spent in that area by the different crew groups. So that is the base for the study, and in phase 2 we are actually we're still working with the QRA assessments by optimizing our design and also detailing it further as we started actually 1.5 years ago, I think. So we have learned something about the system, so we are applying more details to the design, which creates different results from the QRA. And we've also added additional risk analysis to the project. We are reviewing output of hazards and major incidents. We're doing a study of the venting of ammonia, a big study on dispersency study in the engine room of release gas, an impact study seeing what does it take for a large vessel colliding with one of our reference vessels to actually reach the tank in case of a collision, and last but not least, a big additional part including the human factor part, which is definitely important in this respect. Where we have done that's actually also done by Lloyd's, critical task assessment, work environment risk assessment, and an illustration of the competency developments. So we are creating the full picture of the risk, and this is the 3 reference designs. Container vessel, where we have chosen liquid storage, so atmospheric pressure. That's because on container vessel you want to minimize the space used for fuel, so we have chosen the most space efficient fuel storage system. The bulker, initially with a fully pressurized tank system located after the accommodation in order not to take up cargo space, which is seen on the container vessel, and a tanker with tanks on deck on the forward part of the accommodation. It was also to see what's the difference in risk related to the type of containment system, where the liquid storage has the least risk, but on the bulker it actually showed that the fully pressurized tank system just next to the accommodation had too high risk levels. So the design has been changed for that one to a semi-refrigerated system with a 4-bar storage instead of 18-bar. Thanks. Next slide, please. Yeah, and the location specific individual risk shows this heat map, you can say, where the biggest risk areas is, by no surprise, the fuel preparation room and tank connection space, and that's where you have all your ammonia containing equipment and your pipes, but all with a single barrier, so to say, single wall pipes. So of course those are the most risky rooms, you can say. Outside that room, the pipes are assumed to be double wall, at least in the engine room. And as you can see, there's different level of risk compared to the tank locations. So on the container, that's in the cargo hold. That is not the case for the tank and bulker, where you see higher risk on the deck, for example. And interesting thing on the bulker, the accommodations, which is one of the safest areas on the other vessels, has a high risk on the bulker due to the tank location again. And the engine control room has proven to be the safest place. actually. So on the next slide, we'll see the individual risk, because you're not spending all your time in the food preparation room, but this is the different crew groups and the related risks. So that's again the risk of fatality due to an unintended leak in terms of 1 in N per year. And the risk is to, if it's below 1 to a million, you're actually you don't need to do anything further. And if it's above 1 to 10,000, you need to implement safety measures to reduce it to be between 1 to 10,000 and 1 to a million. And as you can see, the risk level for the engineering or the engine crew is rather high, and that's why we need to conduct this ALARP process, where you bring it down to as low as reasonably practical. And you can see the orange illustrates the results after implementing some risk reducing initiatives. And this is could, for example, be to split the fuel preparation room in several rooms. So when you're working on, for example, the fuel supply system for the main engine, you're not exposed to a leak coming from the fuel supply system from the auxiliary engines. So that is a way of reducing risks. And we are still working on this, so it's ongoing. So it's preliminary results, as you see here. Yes, next slide, please. Yeah, that's actually what we have concluded is that as we see now, the risk is there, but it's manageable with the proper design and safeguards. We are still, however, close to the maximum level, so we need some further initiative for risk reduction. And we've also concluded that the crew training, the human factor part, is equally important in combination with the engineer solutions. And the QRA model, if see what is actually driving the risk level, that is the number of leak sources where you are in vicinity to, you can say. And when you have a leak, the flow and the pressure and the volume of that section, that is in the case calculated, the leak calculated from that part is of course has an influence. But then again, if a leak occurs, the chance of escape, meaning that that also includes the design of the room, but also if you're wearing PPE or not. So that is driving the risk. And what can you do to mitigate it? That is some of the initiative we've implemented is ventilation of the rooms, and of course restriction of access to the areas, moving the bunker station away from accommodation, but also implementing water curtain and spray systems, and applying initiatives like when you have a leak, the accommodation is made safe by recirculation, and as I mentioned, double water piping. So this study has contributed with some insights to what drives the risk and what is also possible to do to get the risk below the acceptable or max acceptable limit. Yeah, and I think the findings from this study can be used in future designs like the NoGAPS. Thanks a lot.
Thank you, Klaus. I think what we'll see later as we start to dive into the NoGAPS concept and some of the aspects of the hazard, that we do consider some of these aspects. And I think it's great as we're able to develop some different ammonia fueled vessel designs that we can build in this modular knowledge from other projects here. There are a number of good questions coming in as well, Klaus. So take a look as we go through the other presenters, and you can prepare your responses, and we'll come back to them towards the end. All right, now I would like to introduce Yunito, who's a deputy manager at NYK Line and also a secondee at the center. He has a background in naval architecture and has experience working on new build and conversion projects, as well as ship management at NYK over the last 10 years. before being seconded to the center. He is part of the core NoGAPS team, driving the design and development in collaboration with the ship designer. So with that, Ito-san, I'll hand it over to you for your presentation. Thank you.
Okay, thanks, Thomas. Then next, please let me introduce the vessel's basic design of NoGAPS related to safety concept. First of all, this slide shows the design requirements for NoGAPS. Cargo tank capacity is about 22,000 cubic meters in total, with 5.3 bar of design pressure. NoGAPS is a multi-gas carrier, but it's planned to primarily carry ammonia as cargo, and it can carry all the listed cargo here, including propane, butane, etc., etc. The principal voyage is being assumed to be round voyage between Gulf of Mexico and Norway, and the endurance requirement fulfilled only by ammonia fuel is 12,000 miles. The vessel is equipped with 4 fuel tanks on deck. As this vessel is multi-gas carrier, fuel tank needs to be independently installed from the cargo tanks. However, of course, the vessel is so designed that ammonia transfer from cargo tank to fuel tank would be possible. Another distinctive aspect of this vessel is ammonia bunkering capability. In order to secure future business flexibility of this vessel, additional ammonia bunkering capability is also to be studied as an option. In addition, although this is not novel aspect, the vessel will be designed based on ICE Class 1A for addressing the port regulation in Norway. Next slide, please. Currently, we have completed the feasibility design phase, which consisted of an evaluation of the accommodation location and machinery configuration. And now the initial design phase and optimization phase are ongoing. We have selected after accommodation as a result of feasibility design phase, and the reason is as per this comparison table. From the ammonia leakage on deck during ocean going point of view, forward accommodation would be nicer exactly, but from almost all the other aspects, we consider after accommodation would be better, such as cost, vertical motion in accommodation, engineers' daily inspection and maintenance, including alarm responses, fire response in emergency, etc., etc. Next, please. And this is the current NoGAPS general arrangement and the main characteristics. Length overall is 160 meters decided from port regulation, and equipped with 3 bi-lobe cargo tanks and 4 deck tanks as ammonia fuel tank. Bow thruster, fenders, and the 2-stroke engine with CPP are to be equipped with by taking bunkering capability into consideration. Next, please. As NoGAPS is multi-gas carrier, IGC code is applicable. By taking into account the fact that cargo tank's dome area of existing ammonia carrier is located at the open space, dome areas of fuel tanks are also designed as open space, and this has been confirmed to be acceptable from rule requirement point of view as well. As a safety measures for accommodation, enclosed breach wings, water spray in accommodation forward, and aft air inlet are considered. In addition, automation concept in case of gas detection at air inlet of accommodation is still under consideration. Vent masts for cargo system are located at forward, and vent masts for fuel system are also led to the same location. And ventilation outlet for fuel handling room is considered to be located at forward upper side of cargo handling room. Double wall pipe is to be applied to fuel pipes, at least in engine room, but as for fuel pipes between fuel handling room and engine room, it's under discussion. Next, please. This is NoGAPS machinery system concept. Ammonia fuel is applicable for two-stroke main engine only, and shaft generator is equipped with so that electric demand during ocean going can be covered by shaft generator only. We consider this configuration can contribute to mitigate the risk of ammonia. Hopefully, biofuel will be available for the use of generator engine during maneuvering and cargo operation in port. As ammonia-fueled boiler is still under evaluation, conventional boiler is considered for this project, and liquefaction plants are to be installed for both cargo and fuel tanks. Next, please. This slide shows the current plan of managing ammonia emissions on board. As I mentioned, a boil-off from fuel tank is to be managed using fully redundant reliquefaction plants. And the ammonia mixture during nitrogen purging for fuel system is to be catched by water catcher or a chemical absorber. Management of tank venting using GCU is under discussion. We are inferring that SCR would be needed to install for addressing NOx emission, but we haven't fully discussed about ammonia emission in exhaust gas from the main engine because engine development is still ongoing and the emissions from ammonia-fueled engine is not known yet. Okay, that's all from my side. Thank you very much.
Thank you, Ito-san, for that. And I will now be continuing the discussion here and going through some of the hazard outcomes from the latest risk assessment workshop, including an introduction to the regulatory approach that we've taken here and how we consider the hazard as part of the overall ship design process. So first of all, before jumping in on the regulatory approach, it's important to note that gas carriers are treated differently than other potential ammonia-fueled vessels. Firstly, gas carriers and the NoGAPS project is using the IGC code as a basis, whereas the other ammonia-fueled vessel projects would typically be using IGF code. We can talk about some of the main differences here as part of the hazard work, and also you could see this when Ito-san presented the safety concept, where the cargo area is quite a significant part of the vessel and is considered a hazardous zone. So most of the fuel tanks, the fuel preparation and handling, as well as the piping, all of that is within the cargo space, which can be covered by IGC code. Within IGC code, there is a chapter within that covers cargo as a fuel. This was originally mainly written for methane. However, it can be applied to other fuel products. In particular, though, IGC code prohibits toxic products. And this is where you need to now utilize both the class rules as well as engage the flag administration when you look at approving ammonia as a fuel on gas carriers with IGC code as a basis. DNV rules does allow for this, accepts it on a case-by-case basis, but you need to have agreement with flag. The ultimate objective here, when we look at the project and also the risk assessment, is that we are showing equivalent safety levels as methane or LNG cargo as a fuel. And this equivalence needs to be shown, and it can be shown in different ways, depending on class and flag that you engage. But at this point in the design process, where we are still very high level in the review and the early design documentation, we are taking and have accepted a hazard base, a LARP, or as low as reasonably possible principle, where we can demonstrate the risk levels of ammonia as a fuel relative to methane. But this is just a starting point and needs to be further analyzed and discussed to ensure full compliance as the design progresses. In terms of the methodology used for this hazard, it is a team-based review process where you get a lot of highly experienced people from different areas, from design, from operation, from safety aspects, and they systematically go through the hazards, the major accident hazards that can be identified on board, what the causes of those are, the potential preventative measures, but also what are the consequences and the mitigating measures associated with that. There's a structured process here where we go node by node, where we define the different aspects of the ship design that this assessment covers. Now, because a traditional gas carrier is already, an IGC code is already set up to be able to approve ammonia as a cargo, the novel or new part of this design is limited to the ammonia as a fuel aspect. And that was the focus and has been the focus of the hazard. Okay. This risk matrix provides a high-level overview of the risks identified and which area of the risk matrix they are in. Here we're looking at frequencies, so the likelihood of something happening, and the severity or consequence of that. And when we look at the top risks that have been identified, they are divided into a few main areas. First of all, we have some additional fuel tanks. Ito-san identified those 4 fuel tanks on deck. There is a risk that we could lose primary containment, either due to a fire, explosion, impact, or dropped object. This is something that needs to be considered, even though it is still technically defined within this cargo zone and can be treated as a cargo tank under the IGC code. The fuel handling room, though, however, is a unique aspect here of this design, and as Klaus mentioned earlier, is one of the higher risk areas on board. This can lead to leakage of valves, flanges, pipe ruptures, internal leakages within equipment, and also things such as trapped liquid. And the fuel handling room is really critical in an area where we are particularly focusing our risk mitigation measures. Ito-san also mentioned that there is a pipe connecting the fuel handling room to the engine room. This high pressure fuel pipe is of particular interest here in terms of the risk of rupture. If that pipe is ruptured, there's a certain amount of ammonia that could enter the accommodation area or on deck in different areas. On the same side of things, if you look at the engine room aspect, if you do have a pipe rupture in the engine room, there is a certain amount of ammonia within this high pressure pipe between the fuel valve train and the engine room that can be now put or released into the engine room. And so these are the main types of risks that we've identified here as part of this. Next, if we go on to where are we currently investigating, where are we looking at the different mitigation measures, where are there opportunities to continue to reduce, we've divided these into 5 main areas. First of all, as mentioned, the fuel handling room is one of the riskier spaces on board. And in particular, we want to look at how to mitigate potential leakages of ammonia or ruptures of pipes. In some cases, it might be preferred to use an automated ventilation system to treat that instead of such as a water system. Ammonia reacts with water in different ways than other types of fuels. And in certain cases, it might be preferred to use alternative systems. Same thing from a firefighting perspective. In some cases, we might want to look at other aspects such as CO2 or foam, for example. Klaus mentioned division into smaller spaces is one way to reduce risk. And this is one thing we're looking at in NoGAPS as well. And generally, we're looking at minimizing the amount of time crew spend in this fuel handling room. One example is to look at self-cleaning filters, for example. Can they handle that on their own? Or can that be handled in different ways to avoid people going there in person on regular basis? There are also a lot of uncertainties right now around how to deal with ammonia releases, or what will the ammonia emissions be coming from the engines. We are looking at the accommodation area in particular, how we can protect crew against any type of release. There's also current ongoing development around this water catcher chemical absorber that's built within the fuel supply system. What this does is ensures that ammonia is not released to the atmosphere during normal operational procedures such as fuel changeover or shutdowns. As part of this process, there's also an ammonia water solution that needs to be managed as well on board. The emissions from ammonia engines, dual fuel engines, are not yet fully known. Ammonia slip could occur, and this is something we need to monitor closely as well. On the engine room side, there is special consideration to the piping in terms of the length and the routing coming into the engine room. We want to reduce this amount of ammonia in this pipe as much as possible to reduce the risk in the engine room in particular, as well as on board the vessel on deck. From an emission reduction perspective, there's also other types of emissions coming from dual fuel engines potentially. We know NOx will still be something that needs to be managed, and for that, an SCR is planned. There's also the potential risk of N2O or nitrous oxide emissions. At the moment, it's expected to be handled as part of the engine design, but there's still some uncertainty about that as well. And on the pilot fuel perspective, we do want to minimize this as much as possible. And as Ito-san mentioned, to prepare for biofuel as an alternative here to truly get down to zero emission. Energy efficiency, finally, is important for this vessel, not for the typical reason in terms of reducing emissions. It's mainly focused here on how do we reduce the amount of ammonia we consume. Because if we're able to reduce ammonia, we're able to reduce our OPEX, especially for fuels that we know will be more expensive than the fuels that we have today. And so we're looking at a number of aspects there related to energy efficiency to make this the most energy efficient vessel and to reduce the amount of ammonia. All right, that was the quick run through of the presentations for today in terms of the background material. I see a lot of good questions coming in. I haven't been able to keep track of all of them, but we will get through as many as we can here with the panel as well as with the presenters who presented here before me. But before we do that, I do want to introduce some of the new panel members here that we haven't been introduced yet to. Firstly, I'd like to introduce Dorte Jacobsen. She is the head of the Emission Reduction Department and Fuel Lube at MAN Energy Solutions. She has worked 25 years in R&D of large two-stroke engines, and she's involved in a number of industry organizations, as well as being part of the NoGAPS team here. We also have Frederick Lindfors. He is the project manager in engine R&D at Wärtsilä Marine Power. He's based in Vaasa, Finland, at the new Sustainable Technology Hub there, and he's working on enabling the sustainable fuels through innovation and technology and powertrain solutions. We also have Sven Rolfsen. And he is a naval architect with over 10 years of experience within shipping. He's worked in technical management of chemical tankers and is the project manager leading the NoGAPS ship design efforts at Breeze Ship Design. And then finally, I would like to introduce the last new member here of the panel. His name is Mayank Bhatt, and he is a fleet manager at BW Epic Kosan. He comes with over 26 years of experience combined in the marine industry, both at sea and on shore. He's a master mariner. He sailed on all types of LPG carriers in rank, and he joined BW Epic Kosan in 2017 and recently took up the role as fleet manager here in HSE and compliance in 2021. So with that, welcome everyone. We have the first 4 here panelists where I would like to start with a few general questions here to get your input on, first of all, what's been presented, but also your specific aspects here of the NoGAPS design. And then from there, we will jump into some of these questions that I see coming in. So with that, I will like to start with you, Dorte, and Frederick here from your perspectives as engine developers and the ones focused on the different technology aspects here. When you look at an ammonia fueled vessel design, and in particular NoGAPS, what safety concern has the highest uncertainty at the moment that needs to be further developed along with some of these other ammonia fueled technologies and designs? So maybe I'll start with you, Dorte, from the MAN perspective.
Well, for NoGAPS, we are using DNV as the class and also representative for the rules for safety. But on a general note, I would say that when being a technology developer, we would find it very nice if the regulators and the industry agreed on levels for example, for emissions, both from the engine, but also from all the other systems used on board.
Yeah, thank you, Dorte. So you're referring to things like class guidelines for emissions out of the engine exhausts, for example, in different levels.
Yes, unified class rules, not just one classroom with one limit from DNV, another set of class rules from Lloyd's with other limits, and same from all the other classification societies, until the IMO at some point will give general guidance.
Yeah. Thank you for that. I think this is one of the challenges of being kind of on the cutting edge and looking at a novel ship design, and is that we don't have these prescriptive rules that we can just follow. We have to develop these technologies kind of in the uncertain environment here that we have. Frederick, what do you see? From your perspective, you're also developing ammonia fueled engines over at Wärtsilä.
Yeah, yes, we are developing ammonia fueled engines, but we are also developing fuel systems for ammonia. And one of the things that is an uncertainty is how to handle the vents and releases. And development is ongoing on these systems, which can then handle releases and decrease the releases to non-dangerous levels, so to say.
And when you say releases, Frederick, you're referring to kind of releases as part of the normal operation of the vessel?
Yes, normal, and also leakage situations where you have pressure relief valves opening and such things.
Do you have any recommendations on how to approach that?
Well, the most important thing is to reduce the level, and then it is how to do that. There are different ways, and
yeah. Okay, thank you. Yeah, at least within the NoGAPS design, and this is also something that gas carriers might be handled or treated a little differently than other vessel types, which is that there are some levels of releases from a cargo perspective when you are doing certain operations with a gas carrier. Now, will those types of releases be accepted as with ammonia as a fuel on other vessel types or gas carriers going forward when you consider that? I think that's a bit of an open question to some degree at the moment. So thank you. Thanks, Frederick. So we had those two perspectives coming from the engine maker, from the technology provider of the different equipment. Sven, I'd like to turn it over to you quickly, because the ship designer here is an integral part of the overall ship design, and you're the one trying to figure out in detail how to make it all work. So what do you see here as the biggest challenge, and how do you try to address it as you're designing the NoGAPS project here?
Yeah, thanks for that, Thomas. First, I want to say it's both a privilege and also our duty to work on sustainable solutions in shipping. And new fuels such as ammonia introduce can be a solution, but it also introduces a range of challenges for the whole maritime value chain to solve. Rules and regulations, crew, equipment and technology providers, shipyards and ship designers all have to adapt to these challenges. And ship designers' role is to integrate all different technologies and solutions into a final ship that in the end handles the way the ship should. Even though equipment and technology providers design systems that are safe in themselves, they have to integrate to other ship systems such as cooling, heating, ventilation, and inerting, and this can give added and unknown risks. There are still many uncertainties, but the alternative design process enable technology development in a safe manner that help accelerate the transition that is necessary. Ammonia has other types of risks compared to LNG, which is sort of the governing safety level. How to evaluate an equivalent safety? That is an interesting question in my view. And the green transition have put focus on energy efficiency overall on board of the ships. The fuel has become more expensive, as you already mentioned, Thomas, and owners and charterers are very focused on fuel consumption. And the focus on reducing energy use in total, where it is possible, that also brings many interesting challenges for us as ship designers. And it's important that we do both to have the best overall result. So that is how we as ship designers see it. For the NoGAPS in particular, we need to design a ship that, of course, will function also very well in the intended trade and fulfill all its tasks, in addition to also use the ammonia as fuel. That is a difficult task.
Yeah, thanks, Sven. I think what we've learned as part of the design process is that the more you dig deeper into the specifics, that's when you truly get to the point where you have these meaningful discussions on safety considerations, what types of mitigation measures and safeguards we have in place. And so I think as we look at for example, the hazard workshop and down into the more detailed design here of the vessel, that's when you truly begin to understand the aspects that need to be looked at in more detail. I'd like to shift over one more general question, and then I think we'll open it up to some questions. I'm going to go to Klaus, you first, after this last question here, so get ready. But Mayank, I'd like to get your insights here. You have a lot of experience on LPG carriers and also from the owner's perspective, when considering the ammonia safety concept and the considerations there, how does an ammonia fueled gas carrier compare to some of these other ammonia fueled vessels? Is this a good vessel type to introduce ammonia as a fuel on, or how do you look at that from your perspective?
Thanks, Thomas. a lot has been said by the other speakers already on how the IGC and the IGF code cover application on these vessels. Firstly, Thomas, just to tell, an ammonia gas carrying vessel or a gas carrier that carries ammonia is built with the most stringent measures applicable under the IGC code to contain, transport, and carry out all legible operations on board. So this vessel is specifically designed to handle liquefied petroleum gas, ammonia being part of one of those. And the compliance requirements for safe handling, is incorporated for these vessels at a design stage. So it's a very mature design that comes out. The other ammonia vessels, ammonia fueled vessels, have a good design, but it's only applicable to the fuel containment, fuel management section. The other vessel could be built to any other standard. So an ammonia carrying gas carrier is definitely the best vessel to be able to handle ammonia, because she handles ammonia as cargo. That is the first part. And the people serving on these vessels, they are highly specialized people. They undergo very stringent training, both as per the STCW requirements and the industry practice. So these are seasoned people who handle this cargo day in, day out. So this is the best set of people to handle IGF grade fuel as well. Coming to the ammonia, being introduced as a fuel, I feel that basis the design, the emergency response equipment, the crew certification, the experience and training, being in line with the IGC code, I think this is the best vessel to go ahead. The other thing is that this vessel trades generally in ports where ammonia is handled. So it's the best suited vessel to go in for ammonia bunkering as well. Most probably these would be the bunker rich ports where vessels would call. So there's no commercial deviation as an owner, to move a vessel out of a trade. So that is how I would respond to your question, Thomas.
Thank you very much, Mayank. And I think that gives a good perspective also from the operator's viewpoint as well. I think now what I'd like to do is to start addressing some of these questions. I'd like to get maybe Klaus back in here so we can see him. And maybe Klaus, one of the first questions here, Klaus, is that I know you've been looking at other type of vessel types, other ammonia fueled vessel designs. How do you view the design and development of those relative to the NoGAPS project, and where are the main differences here when you look at an ammonia fueled container vessel or bulker relative to a gas carrier? Can you give some initial insights there on that?
Yes, I mean, the ammonia fuel carrier are definitely some steps ahead, because it's designed to have ammonia on board. And furthermore, it operates at terminals where ammonia is expected, where, for example, container vessels is at container ports with the cranes operating above it and stevedores being on board. So the complexity or the safety measures that are maybe deemed enough for a gas carrier is maybe not enough for a container carrier, because a venting situation at a container terminal is a completely different thing than a venting situation at an ammonia terminal. So you could say that starting with the gas carrier, it's the easiest way to get experience with having ammonia on the main engine and maintaining that system. But ammonia is to be applied on more than gas carriers. So there are definitely a lot of other aspects or complexities to be covered on the other vessels. Especially to the crew training competence on commercial vessels, they are not used to the fuel being the difficult part. That's not their key focus, and And furthermore, they operate in areas closer to cities and so on, which makes it, I think, more not challenges, but we need to think about safety measures in another way at a higher level than on gas carriers.
Great, thanks, Klaus. And to continue on to this, one of the questions from the audience: how do you decide what type of tank do you use? Is this based on, each individual vessel type, semi-refrigerated, fully refrigerated, pressurized? How do you make those considerations for your for that study, the safety study?
Yes, it is partly vessel dependent, because as for a container, you don't have space on deck, so you will need a tank, and that tank needs to be as space efficient as possible, and that leads to this atmospheric tank system where you need to keep it liquefied. On a tanker, you have space on deck, so you can use the less complex tanks in terms of C-type tanks that you store on deck. And that again could be either fully pressurized or semi-pressurized. Fully pressurized tanks it's of course easier to deal with, as you don't need any re-liquefaction systems. They're also heavier. So for a tanker, it makes sense to place C-type tanks as you did for the ammonia carrier. The bulker could be either, or maybe you could also include a structural tank on the aft. The liquefied tank comes with a challenge, as you need to maintain the pressure. It was also one of the questions, and that adds to the complexity. You either need to have some re-liquefaction units on board, or deal with it in other ways. And if you have pressurized storage, you have a higher margin of pressure buildup and so on. It's not as critical as a fully pressurized system. So it has an effect on what type of vessel you're looking at and what are the best suitable tank systems.
Is there an aspect here of societal risk if you have these types of vessels in port areas as well, with the risk of loss of containment, for example? And I assume a pressurized release is much different than a fully refrigerated type of incident within a certain area.
That's true. A pressure or a leak with pressurized ammonia it's much more dangerous, as you have two-phase leakage, probably, where liquid non-pressurized ammonia is, you can say, less dangerous. It's just evaporating from the pool. On the other hand, if you are turning around, say, but if you are pressurized, you also have a margin of pressure buildup, where the atmospheric tank, if you're losing your tank pressure management system, you might reach a point where you need to vent faster than if pressurized. But again, that also depends on what is the starting pressure you arrive at port with. So, yeah. But definitely, the liquid storage is definitely the most safe way of storing ammonia.
Okay, thanks. And Klaus, maybe just one follow-up question here. As we look at the, you were talking about the acceptable risk levels, and what needs to be done to reach acceptable levels, or what is the approach here? Are you targeting the the acceptable levels, or reducing the risks as much as possible on these different vessels? Can you explain kind of how you do that, and any of the human factor aspects here as we look at that as a main focus area?
Yes, we are trying to bring the risk down to as low as practically possible. Where, for example, we are looking at even further, say, sectioning of the system in the fuel preparation room, which is the key risk area. So you could also, even though you have split the room in several compartments, you could also have maybe as a part of the fuel valve train encapsulated as well. So you put a box in a box. That could be a way of reducing risk of exposure to a leak. But at some point, it doesn't. Well, it's not reasonable anymore, so to say. But we need to do whatever is possible to, in a practical way, to reduce risk. And as you mentioned, we need to look at what about remote monitoring, simply avoiding entering that room. And I think that's the way forward. Bunkering, doing that remotely controlled, and so on. Yeah.
Okay, thank you. There were some other specific ones, but I think we'll skip those for now, and we can always respond to them separately or come back. I did want to shift gears a little bit and come to you, Dorte, as the MAN expert here on two-stroke engines. There are a lot of questions generally around how is ammonia slip handled? What type of SCR system do you have on board? And what is your assumption around kind of the nitrous oxide emissions? Can you just briefly explain what the assumption is that's being used now right there on how we look at that aspect?
Yes, I can. Thank you. Well, we are expecting that NOx will be formed during combustion. And for the NoGAPS project, we are installing an SCR, a high pressure SCR, which is situated in front of the turbocharger. And we are installing an SCR which is larger than a normal one would be for fuel oil, to be able to install also extra catalyst in case this is necessary. And yeah, I talked about the type of SCR, high pressure SCR, but otherwise the same system as we would normally do for traditional fuels or gas or whatever. And there was a question on the laughing gas. Here we are expecting that we can handle this by engine tuning. So we will do our utmost to mitigate emissions of laughing gas. It is a really difficult or challenging greenhouse gas. So with a greenhouse gas potential of almost 300 compared to CO2. So this really needs to be taken serious.
And on the, thank you, Dorte. We're also getting some questions around this ammonia catcher system. And first of all, there was one question about, will this solution be incorporated by DNV into requirements? DNV, under the guidelines, first of all, they do require an ammonia emission reduction system on board, which this concept, this water catcher concept, can be used to fulfill. There are some questions though, Dorte, and also maybe Frederick can give some insights from his development in the fuel supply systems. How does this type of system compare to other solutions like a gas combustion unit, for example, and what do you do with this water reacted with ammonia afterwards? How do you dispose of that? Maybe you could give some insights there if possible.
Well, the system is very safe and regarded as rather simple. But of course, as you say, it is producing some water with ammonia in it that needs to be handled in some way. And at the moment, our development is looking into capturing this water, and then needs to be disposed of afterwards somehow. But of course, you can build such a system so that you can almost get to the emission level that you want to.
Great, thanks. And then, do you have any experience looking at gas combustion units relative to other or any other solutions compared to this?
No, maybe we can hand that over to Wärtsilä. They may have something.
Yeah, I don't know. I think Frederick might have dropped off the call here. At least I don't see him at the moment. So maybe he'll come back. But for now, let's move on. There were some questions also about what are the current emission limits related to NOx and ammonia to ambient. And at least what I can say is that we are designing it. The SCR, I believe, is dimensioned to tier 3 compliance for NOx, and then the limits for ammonia release to ambient is I'd say is different if you look at perhaps the engine exhaust relative to the fuel supply system. I don't know, Dorte, if you're able to give some input there on what types of targets here we're looking at when it comes to ammonia levels coming out of the vessel.
Well, this is exactly some of the levels I talked about earlier, that it would be really nice if these levels were agreed between classification societies. And we are, of course, aiming for a low level in the engine exhaust, where we are also working on using the ammonia slip as a reactant in the SCR. The level that is coming out, we aim at something like 20 ppm at the moment. But of course, development will show where we will end.
Okay, thank you. I'm done grilling you on questions, so I'm going to move on to Sven over here. And Sven, there's some design related questions here. First of all, around why we chose the bilobe tank here, and maybe you can give some background on why this type of tank, this semi-refrigerated tank, was selected relative to maybe a fully refrigerated option, or also other considerations in terms of the ship design, you know, available space and integration.
So the bilobe cargo tanks was a design requirement in the design specification to start with, which the reason for that, as I understand it, is the cargo flexibility of the ship. If the ship was built only for ammonia, a different type of cargo containment would perhaps be more efficient, given the flexibility you want to build into the ship. The bilobe semi-pressurized, semi-refrigerated gives more flexibility. Versus a bilobe versus strictly cylindrical tanks give a better space utilization and a bigger cargo volume than for the length requirements that we had on this ship due to the port restrictions.
Great, thanks. I see Frederick's back now. So thanks, Frederick. We had been discussing the water catch system and the treatment system for the ammonia as part of the fuel supply, and there was a particular question around how this type of solution, chemical absorber type solution, compares to other options like a gas combustion unit or something else. Is that, maybe you can give your perspective here from Wärtsilä in terms of how you're thinking about the solutions for this type of challenge on board?
Well, the challenge can be to dimension it correctly for the amount of gas that needs to be purged. So that is the challenge, I would say, that you need to start looking at from the beginning. Yes.
Okay, thanks. Thanks for that. We are running short on time, but I would like to go to you, Mayank, because I'd like to get this operational experience in here. There's a number of questions around safety in terms of, you know, what type of PPE should be worn during routine maintenance of the different systems, you know, human safety factors, SOPEP equipment, and response to spills or to the environment or on board. I'm sure you've seen some of these coming in the chat. Maybe you can give your, you know, 2-minute view on generally what is on board gas carriers today and what type of things would be needed here going forward.
Yeah, thanks, Thomas. Thomas, I'll take up the PP question. The PP question, is the PP to be put on board an ammonia fueled ammonia gas carrier would be a direct compliance to the IGC code. So the existing personal protective systems and safety equipment that is required would be there, inclusive of each person being able to, or each person being assigned an emergency breathing device that is for emergencies. But when we look at an ammonia fueled vessel, we increase the amount of the gas suits that need to be worn while carrying out maintenance on these systems. There are various procedures for lockout, tagout. There are additional safety mechanisms in place wherein you make sure that the pipeline which is being worked at, the various fittings, are under no pressure, they're de-energized. The whole gambit of having a safety analysis carried out, job hazard reduction done is there. The PPE for handling ammonia, it's basic PPE that is carried on board gas carriers. But yes, gas canister masks are not allowed. Positive pressure breathing devices are to be utilized. There need to be emergency mitigation measures in place. The human factor analysis would include sustainability in design, ergonomics, lighting, various other factors, which include less fatigue, less ease of working, less exposure, less risk based on the size and the space available to carry out a job safely. That would be incorporated there. Coming back to spillage. Spillage is going to get resolved under the existing SMPEP or the pollution emergency plan applicable to the vessel. The vessel would most probably also have a procedure and arrangement manual, being able to carry some of the cargoes annexed as NLS. So she would have a higher state of emergency response in case of pollution, and she would be designed in a way wherein there would be spray, there would be water spray which mitigates any environmental release of ammonia on open decks. Ammonia is very miscible in water. That would be something there. I see a question on what are the challenges you anticipate when a vessel enters shipyards or repair yards. The challenges would remain same that we see on gas carriers. So basically, the vessel would need to be gas free. There's a specific procedure to be followed when handling ammonia. It's very important to make sure that the dew point of air being used to purge these tanks is in question. You use hot air, you heat your tanks up to 45 degrees, making sure there's no leaching of ammonia into the tanks. Some of the questions, any specific question that you would like me to take? Reaction of emergency shutdown systems would be as per IGC code. So they would require to close in not less than 30 seconds. Anything else?
Yeah, no, that's great, Mayank. I think that gave a good perspective in short time here. We are out of time actually for today, and I would like to thank the presenters as well as the panelists. We will try to address these questions, and maybe we can work with GMF to get a response on a website here to address all of these. Stay tuned for more from the NoGAPS project. We do plan to publish a report soon summarizing the latest work that we've done now during the feasibility phase. You can also find out more about the project on our various websites, both the Nordic Innovation one, the Global Maritime Forum one, as well as the center one at zerocarbonshipping.com. I would like to thank everyone for attending today. And I wish all of you a nice rest of your day. So with that, thanks and yeah, and goodbye.